All right.
Wonderful. All right.
Awesome.
Hello, everyone. Welcome to week 4 of McMed Hacks. It's nice to see a lot of returning faces. And we have 2 speakers today, Dr. Christina Gillmann and Dr. Christopher Deufel. And we'll introduce them in a bit, but first, a little bit of information.
So a little bit, yeah. So let's do a little bit of a recap for week 3. As you may or may not have seen from our email, we have shared a common Google Drive folder that contains all the contents that we developed for this workshop, where you can take a look at for week 1, week 2, and week 3. It has all the workshop Google Colabs in it. It has all the slides and the assignment solutions, the recordings for the presentations, as well as the workshops, as well as quizzes embedded into this Google form, where you can also find the recording. So all of these things are in this one location. And every time we send an email, we link this one Google Drive folder to our email as well. So just please read our emails. Some information that you have missed is probably somewhere in the emails. So I know we send a lot of stuff, but we have a purpose in doing that. So anyway, so last week we had 2 parts of the assignments for week 3, developed by our 2 amazing mentors, Nee as well as Leo. We had 2 tutorial sessions as well, one on Thursday nights for one, mostly North American students, and one on Friday for our European students. And so we see that some of you have attended the tutorials, so we really appreciate that. So we encourage learning by doing in our workshops. So even though we might not be able to cover a lot of code that we have in detail on our Google Colab, we sort of focus more on the higher level concepts for the workshops, but that doesn't mean that you shouldn't look at the code in detail by yourself. And then that's how you're going to learn. So, and then we also try to provide as much information as possible during the workshops, but we only have 1.5 hours, so we can't cover everything. So if you feel like you're struggling with the actual code, so please attend the tutorial sessions, where you can actually ask the mentors about the more details on how the code works and so on. And so feel free to do the assignment. We're going to send the solutions of assignment 3 very soon. And yeah, so every time for us to decide on a tutorial time for you, we send out this when to meet form. Last week, Luca and I had made a sort of a mistake where we didn't make it such that you can select your own time zone, but that's been corrected. And from now on, when you look at the when to meet form, you're going to be able to select your own time zone. So please fill it out so that we can decide the best time to hold our tutorials. And last but not the least, after our talks today, we're going to migrate to GatherTown. The GatherTown is a virtual platform where people, it's kind of like Zoom, but you have your own character where you can walk around in a virtual space, and people around you, in close to you in a virtual proximity, you can see them and hear them. So you can sort of like talk to them just like in real world. So we're going to go have a drink on the beach there. And we're gonna circulate this link right here in our group chat, in our Zoom chat right now, as well as on Discord. So please feel free to join afterwards so that we can say hi. This is it's really good for you guys to get to know each other a little bit if you want to attend the hackathon at the beginning of August as well. So more details are to come. Yeah.
All right. As usual, we are taking attendance. If you're here today, your attendance is taken automatically through Zoom. And if you're not here today and watching the recording, make sure to fill out the quiz after the recording to verify that you watched the whole thing. You may miss up to 2 events, meaning not attend and not watch the recording. And if you attend or watch the recording for all the other ones, you will receive a certificate of completion. All right. We want to give a shout out to our team again. McMed Hacks is a very large workshop series that's bigger than what Yujing and I could plan on our own. So we have an amazing team that helps us organize everything for you guys. We have Marie, Sasheen, Alina, Zachary, Hossein, Elena, Juan, Milosh, and our supervisor, Dr. Enger, who are all helping us. So a big thank you to them.
Yes, and very briefly, this is us again. Yeah, we can move on.
Yeah.
So let's introduce our mentors for this week. So as usual, we have 2 mentors for every week, and today we have 2 new faces. We have Vasu and Jack. What they're responsible for are the following. You can ask your questions on Discord and anonymously or not. And then Vasu and Jack will organize your questions and ask our speakers the question at the end. And they're also responsible for creating this week's assignment for you. And they're also responsible for holding the tutorials for you guys this week based on your availabilities, of course. So let me introduce let me introduce Vasu first. Would you guys like to? Yeah, you guys' camera already on, so you're gonna say hi afterwards. So Vasu is an incoming master's student at University of Toronto, where he's gonna pursue computer science, and he's really interested in the intersection of medical imaging, computer vision, and deep learning. And in the past, he's worked on semantic segmentation on his pathological images into axons and myelin data, and some other medical prognosis using multi-modality data. So Vasu, would you like to unmute and say hi? Are you able to unmute? Oops. You unmuted and I muted you. Sorry.
Yep. So yeah, pretty excited to be here, and hi everyone, and hope to learn a lot from this workshop, and I hope everyone would be having a lot of questions after the workshop and tutorials. So pretty excited about it.
Awesome. I'm glad you're excited. And then we have our second mentor for this week, Jack. So Jack is an undergrad in cognitive science with a focus in neuroscience and computer science. Ultimately, he wants to work as a surgeon and a researcher in experimental surgery. And we're really excited for you to be our mentor this week, Jack. Would you like to unmute and talk a little bit yourself too?
Yeah. Hi, everyone. So again, I'm really excited to be part of this, and I think I have a lot to learn from this as well. And so I'll do my best to get everyone excited at the workshops and answer as best as I can the questions.
Awesome. Perfect. I think this is it for the slide. Yep.
We have our standard rules for the participants. Again, it boils down to be polite and respectful to the participants and speakers. So we strongly encourage you to also engage with one another on our Discord. This is it, in case you hadn't seen it. Today, questions will be asked in the week 4 text channel. Later on, we'll be hosting the tutorial on here as well. But go ahead, and if you have questions to our speakers, post them in this channel. This is where our mentors will be monitoring and potentially answering questions if they know how.
Yeah, the voice.
Yeah, go ahead.
Sorry. I just wanted to say that the tutorials are usually hosted on Discord voice channels. If you haven't been to one of our tutorials, that's where you should go. You can unmute yourself at the bottom, and then usually if you can't unmute yourself, just check the setting of your computer to see if you have permitted Discord to permitted Discord. So if Discord has your app permission for your mic and camera. So that's it. All right. So now we're going to hand the mic to Dr. Christina Gillmann. But first of all, let me introduce her. So it is our greatest honor to introduce Dr. Christina Gillmann. She's going to talk about multimodal machine learning for CT from an example to generality. So she is a scientist at Leipzig. Did I say that correctly? Leipzig. Okay, Leipzig University, discovering the exciting edge between machine learning and medicine. So we're really excited to have her here today. So you can, Luca, you can unshare, and then Dr. Gillmann.
Thank you very much. I'm going to start sharing my screen. So we should be there. Do you see my screen?
Yeah.
All right, perfect. Thank you very much for a nice introduction. It's a great honor for me to be here and be a speaker of today, because I actually never got to be asked to be an invited speaker on any event before. So thank you for that. I will show you a quick view on my content today. So first, you may ask yourself, who's this Christina Gillmann? And I'm going to say some words about that. And then I'm going to go for the example that I brought to you today, which is one of our most prominent and most recent research projects that we have, which is multi-modal lesion prediction based on CT scans. And we're going to talk a bit about the data, the learning model, some results, visualization of the neural networks that we use in future work. And I also want to share with you some lessons that I personally learned, because that was actually the first neural network approach that I ever used in my life. So maybe there are some lessons that I learned that I can share with you that make you not run into the same problems that I have been running into. So yeah, who am I? Here's a picture of myself, because I wasn't sure if you guys can see me talking. And I'm a scientist at Leipzig University, which is in the eastern part of Germany. And I'm part of the signal and image processing group in the computer science department. And I basically did my PhD in computer science on the topic image processing under uncertainty. And at that point, I wasn't actually not right much into neural networks. It was actually very classical image processing, like filters and histograms and all those things you learn in a classic image processing lecture. And I'm teaching on the border between computer science and medicine around, let's say, 8 years. I usually give lectures such as image processing for medical imaging, or visualization and or analysis techniques in medicine in general. So that's why I usually teaching. And for just a personal side note, I love doing fancy cakes. So here's a picture of our university building. So Leipzig University is pretty much distributed all over the city. But this is the main campus, and this is actually part of where the computer science department is located. I wanted to show you this fancy building because it's really interesting. It's actually supposed to resample an old church that has once been located at this place. And the architect thought it might be a good idea to make it look really fancy. And for my research in general, what I'm doing right now is I try to mix different things. I actually try to mix machine learning with visualization and uncertainty analysis. And we will come to the point why this actually makes sense to think about all these three things at the same time. All right, so let's start with the multi-modal lesion prediction. I'm not sure how much you know about medicine, so I will go quickly through the problem that we are actually targeting here. A stroke is the second leading cause of disability worldwide. This is, and it will become, there is a tendency that it actually will become the leading cause of disability worldwide, because people tend to eat too much, drink too much, do not move enough. It can also be a part of a genetic problem, but the problem right now is that society becomes more and more old and is not really healthy at all. So what can happen there is a stroke is caused by a blockage in the supplying vessel of the brain. And what happens is, if you have this stuff accumulating into your vessels, there's the point where the vessel cannot really supply the rest of the tissue anymore, the tissue that is surrounded by it. And this can result in that brain tissue may die if this blockage holds on for too long, or if the blockage is really bad and there's really no supply for this brain area anymore, the brain tissue literally dies. And what clinicians are calling this is a lesion. And the idea of the project that we're having here is that we can predict these lesions, because the problem is when you're going to clinics and there's and you may have had a stroke, and there will be some examinations, and they will look, is it a stroke or not? And they can pretty much say if it is or not. But the problem is at that point where it's super current, you cannot really say what part of the brain dies and how big this lesion will become in the end. And this is what we're actually targeting in this project. So what is the data that we're using? Right now, we are using a prototype data set, and this prototype data set contains 170 patients. And the idea is that we will have soon, and with soon I mean really like in about a month or so, a final data set that contains 300 patients. It's 3 times labeled by 3 different doctors. And there's going to be a supervision step where one doctor goes through all the labeled data and rechecks if everything is labeled correctly. So you might imagine this is tons of work. It's like there are 4 or 5 clinicians are working on this to make sure that the data is corrected as good as possible. And our data set contains for each patient different types of data, which are shown in this figure. So the first one is a native CT scan, pretty much the general CT scan that you can get, and there's no additional like contrast bolus or something in this acquiring process involved. Then there's a CTA, which is a CTO angiography, which means that there's a contrast bolus injected so that you can see where the vessels are actually located in the brain. And this is very important for the stroke imaging, because I told you it's a blocked vein. So there's already a hint on, if you do not see the veins anymore on this image, there's pretty much a hint that the blockage is something going on in that direction. There's also CT perfusion, which uses another contrast bolus. And this one is actually going more into the tissue. And the interesting part of this modality is actually that it's a little, and it's really a little tiny video, because it actually does not have only one image. It holds 16 images, and it shows how this contrast bolus separates into the tissue. And with that, you can generate different masks. So usually the clinicians do not really look into those videos in general, but what they do is they use all these 16 images from the mini video and generate some masks. And these masks contain information, for example, how long did it take until the highest point of contrast bolus reached in a specific voxel of this image. And this is the acute stroke imaging. This is what happens when you go into clinics and they think you've got a stroke. This is what they really do, and this is how they can decide if it's a stroke or not. And then what I told you before is we cannot really, at this point, we cannot really say how the lesion will look like in the end, because there may be parts that can regenerate, although they actually look pretty bad at the point when you get into the clinics. On the other hand, there are parts that look not too bad, but still they die, and it's not really clear how this works. And in the end, they're going to do a follow-up MRI in this case. And this follow-up MRI is actually only used to generate a ground truth for our learning. And the really interesting part about our approach in this project is usually what people do, like there are a lot of works that try to make lesion segmentation based on CT scans. And what they usually do is they take this input, no matter how many modalities they have, there can be one more, one less, stuff like that, but that's actually not the point. But they work with this acute stroke imaging database, and based on that, they do a ground truth. And what we are doing here is we take a completely other picture that has actually nothing to do with this acute stroke imaging, besides that it's the same person, but it's usually generated 2 or 3 weeks after the acute stroke imaging. And in this follow-up MRI, the ground truth is generated. And the funny part, or the super interesting part of our project, is that our neural network that we're training will never see this follow-up MRI. It only sees the acute stroke imaging, and of course, we're using the ground truth that we generated based on the follow-up MRI to do the training. So this is the very, let's say, unique point about this project. So we're pretty much talking about a prediction here. We're not talking about a segmentation task, we're really talking about prediction tasks. Okay, so when we got all that data from our clinical partners, we had a lot of questions, like not only we, but like the entire team made of clinicians and of computer scientists. So we've been wondering, do we need all the modalities? The doctors, they do these images because it's a routine. The clinic says this is what needs to be done when you come in with a stroke. And everyone's wondering, do we really need all of them? So what we also wanted to know is we wanted to predict, or the idea of the project was to predict the acute lesion and how it will evolve and how it will look in the end. And we were wondering, can old lesions be separated from these new lesions? Because in my point of view, when you look into the images, they look very different. So I thought, okay, probably the neural network will be able to separate them. We will see later that this didn't really work. We wanted to know, even if we need all the modalities, which one is actually the most important, or which are the most important? And this approach of predicting and not using like actually the MRI that we created in the end in the training process, we had no idea if this is working. So we were just like, okay, we need to try it out. And I'm going to show you a little bit of the journey that we made so far to see if it worked or not. What I want to show you, because I was not entirely sure if you, how much you already know about machine learning in general, is whenever you use images to do some prediction, classification, segmentation, whatever you want to do, you will need some filter kernels, because these filter kernels will be trained by the neural network, and these filter kernels will be responsible to figure out or to learn what the neural network is actually able to predict or to classify, and they will actually encode the information that the neural network needs to achieve the task that you give to the neural network. And the idea is that the neural networks finds filter kernels that are actually matching with the input image. So for example, here you can hover this over the image, and then in the corners of the horse you cannot do that. So you can only do that for the inner 3 pixels. And what you can do is you can see how many pixels do I have that are overlapping. So if I'm putting this in the upper left corner, we will see that we have 3 pixels that match with this current kernel, and we can put a 3 here. This also holds for this corner pixels here, and for the center one, we get a really, really nice overlap where we have 5 pixels that are actually the same. So on the other hand, if we're using this as an input and still the same filter, we see that we can actually not really find a lot of overlapping here. So every pixel that's going on the square here will produce 2 overlaps, and even the one in the middle will not get any overlap at all. And so what we learned from here is the filter this filter actually fits much better to the first input image than to the second input image. And this is actually the idea of these convolutional neural networks, that they try to find the best filter to do a classification and find an overlap in your data, and therefore try help you solve your task. The model that we're using here is actually a very specific convolutional neural network model, which is called a UNet. And I will shortly explain to you how a UNet works. I really hope you have some basic knowledge on neural networks so far. So what do you usually do when you do classification? Let's say you want to know if you can see a cat or a dog in a picture, and then you usually just need those two answers. It's like there's one answer that might be cat and your answer is dog. And this doesn't work in our case because we want to know where on the image we can see the lesion. It's not only a classification task, it's a segmentation task, a localization task. And this UNet is actually, we didn't invent this by ourselves. This is, let's say, for segmentation tasks in medical imaging, a very well-known network that is used, and with, let's say, more, I mean, there are tons of units out there, but they only vary in, let's say, smaller things on how you will set up the layers and stuff like that. So the traditional the UNet that we are watching here, it gets an input image, and what it does convolution. It does the convolution that you traditionally learn when you do a classification task until you end up down here, and this is called the bottleneck. And from this bottleneck, you are actually expanding your image back so that you also get an output image, and that you can say for each of your output voxels, there's a specific probability that this voxel shows a lesion or not. And this is like an extension of a traditional convolutional neural network, and it's separated in a convolutional path, which is, let's say, that what you should know about neural networks so far, and a deconvolutional path that is exactly the opposite of the first operations, and making sure that you get an image out of this. So let's come to some results. Here you see on the top row, you see some ground truths. And what you see here is with different learning rates, some results of our prediction process. And I was by myself really surprised that we actually got really nice results. So there's one thing that you may have encountered, which is this example. So first of all, yes, we have patients where we do not really have a lesion in the end because there are some specific surgeries that you can do to try reopening the vessel. And with that, being able to give the supply back to the brain. And if you're doing this really, really quickly, then there's a high chance that you will not have a lesion at all in the end, although you had a stroke. And the problem is what you see here, the network tries to predict some lesion in this patient. And the problem is those are only 7 patients out of this 117 patients that we actually have been talking about in the beginning. And the problem is the network does not really count on these 7 patients. It's more counting on all their lesions and all their brightness and all their different shapes, what he tries to predict. So we have to find a way to go around these cases or to deal with these cases. We do not want to discard them, but we need to find a way to actually work with them. What we already saw is the smaller you set your learning rate, the longer it actually takes until you get to the point where you can really find a lesion and separate the lesion from the rest. And what is also very interesting is that it starts evolving from the original images. So these are actually really looking close to one of the image modalities. So you see something like headish shape, and then it goes further and further and further and develops into a real lesion. So that these were some interesting points that we figured out about this training process. What I also wanted to show you is that we actually got a really nice result for the first try. I mean, it was a simple UNet that we tested. We didn't even have multiple channels for the different modalities or some other fancy things. It was really, okay, let's use this UNet that has been proposed and see what's going on there. And what you see here, if you are looking at the area under the curve, with the training set, I mean, of course, and that's not something that you should use as a benchmark, but here we get really nice AUCs. The highest that you can have is 1, and what would be perfect or desirable would be all the curves of the patients are going literally like from here directly to 1 and just keep there. And everything that's not, or everything that goes further away, like this red bar here, actually means that for this patient, the prediction didn't work as well, or that well. And then you also see the validation data set. And here, of course, it's not as perfect as a training data set, but we still get, depending on the learning rate that we're using, actually pretty nice results. And we can end up with an accuracy of 68%, which is 86%, which is actually pretty nice, given the fact that we're having this test data set and the fact that we actually just used one model and we didn't think about any refinements so far. Okay, but of course we continue then, because 86% is not the end of the line, what we hoped. And of course, the first thing we tried was actually using data augmentation. And for the data augmentation with the resulting test data sets, we were actually able to go further a bit, and with the deformation and rotation, using both of them as together, we were ending up at almost 88%. So let me give you a very short description of data augmentation. So I told you the data set isn't really big. I mean, 170 patients, that's not perfect at all. So what you're doing with data augmentation in such cases is you are generating new data sets based on the data sets that you already have. And this can be done by just putting a lot of transformation on these data. Here we use deformation, which means that let's spread it a bit. Let's take the x-axis and squeeze it a bit, stretch it a bit. There's also rotation, where you just use the image and rotate it into all directions. And of course, you can have an arbitrary combination of both. And this show in our example, this showed that we got the best results out of using deformation and rotation at the same time. Okay, so the next thing that I want to talk about is the visualization of units. Our medical collaborators have been really happy with predictions that we made at that point, although especially as they knew that we didn't do really fancy things at that point. But what they've been not so happy with is that we just gave them the results and they were like, okay, so how did you determine this lesion? And we were like, I have no idea. And we're like, why do you not have any idea what the network did? It's like, okay, it's a network, it's a neural network. Networks are black boxes. I cannot look at, I mean, I can look into that. I will show you in a second, but it's not like I can naturally look into that. It's not like a function that I can draw on a plot and say, okay, here we see things and we can examine that. So we need to find a way to show how the neural network makes the decisions, especially in medicine. You will never ever find a doctor that just goes with your program and your program says, okay, do the surgery, and you will be like, yep. So there needs to be a reasoning behind that. And this is the idea of, we need to visualize the unit, because also our doctors wanted to know what is going on there and how does the network come from the acute stroke imaging to the predicted lesion. So we also had some questions here where we wanted to know which voxels lead to the decision of the network. Like, is there any specific area in the brain that does some contribution to this process that is really important? Which patients play an important role? Are there patients that can be generalized more than others? Which modality play an important role? We also had that question before, like, is there anything where we can see if a modality helps more in the training process than other modalities? And are there any features that can be identified in the different layers of the unit where we can say, okay, this is actually something that a neural network is looking for, and that you also should be looking for when you're looking in this data. So those were the questions that we actually developed. And we tried to visualize the unit using two different approaches. One is the activation map, and the activation map describes the importance of a voxel to contribute to the resulting prediction. So there are mathematical formulas forms that behind that, but I want to put them on slides because I never like to have formulas on slides. There's the saliency map, and this describes the degree of activation in the backpropagation process, which means like how much does a value make your network change its values during the backpropagation process. And what we also could do was summing up all these values in each layer to make sure that we see from all channels the results. So what did we get out of that? It was actually really interesting because in the first layer of the network, we were actually really able to see that the network is looking for the head of the patient. So it was really, okay, everything that was outside of the head was not really considered in the training process. Then in the that's what you can see here in the top row, and then in the next level or in the next layer, we saw that the network started really like breaking down the head into different structures. So we had here the impression that it was separating left and right hemisphere of the head. But the problem is, the further you go down into this neural network, into this UNet, the more channels you get and the more patient specific they become. So you cannot really make abstractions anymore at this point. So our idea was that we use a brain map. There are standardized brain maps where you have different areas of the brain that are usually responsible for specific functions like speaking or movement. And what we were able to do is we were able to see, is there any part of this structure that was activated very prominently? Is there any, where does the lesion actually lie in this part of the brain? So if you see, okay, the lesion here that you see here was located in the putamen, and putamen is actually one of the brain structures that is very important for speaking. So you could assume that this patient will probably have a lot of problems with speaking, and that you should send him directly somewhere where he retrains that, basically. Okay, so what did we find out while visualizing these units? We found out that intermediate layers are similar at the borders across all patients, but they vary in the center, and that actually makes sense because usually the lesion is located somewhere in the brain, which is located on the images in the center. The channels contain patient-specific data, which is actually still really hard to interpret. So we found some things that we were actually able to visualize, but not all of them are abstractable to all the patients or the data set in general. The channels become, of course, more abstract, and as I said, it's still not entirely clear what they encode. But what we found is that the angiography activates more than the native CT scan. And this is actually really surprising, but because when we did the training with our original unit, we actually tried different settings. Like we just discarded one of the image modalities, and every time we used CTA without any other imaging modality, the results of the prediction were really bad. So it's actually really surprising that CTA activates a lot in the neural network, although it's not really part of making a good result. CTP activates at most, and we already had that when we had the neural network. Every time we included CTP in the training data, the neural network had a better performance. Okay, so let me come to lessons that I learned. You need a close, and I don't know which else settings I should put under this word to highlight it further. You need really a close collaboration with clinicians. I'm not a doctor, and I mean, they give me the data, and I can of course somehow relate and learn a bit on how strokes work and how a lesion looks like in the image. But in the end, it's up to the clinician if the results that you produce are correct or not. And to figure that out, you need a close collaboration. So we're pretty much speaking every, let's say, at least 2 weeks about, okay, this is how we progressed. This is what we did. They also asked us, like, how do you need the data? The pre-processing is actually done by them so that they can make sure that the pre-processing is not messing with our data or losing some information. Really, this close collaboration is the most important point that you need if you're setting up such a project. I also really want to recommend to visualize your network, because although we are computer scientists, I learned so much about my network when I use these visualization styles. And I really want to recommend it to every one of you. Also, uncertainties everywhere. I didn't talk a lot about this in this talk because I did not have the time for that. But as I said in the beginning, every data set is labeled 3 times by 3 different doctors. And the labeling is really different. The lesions that they detected, they look pretty much different. So we somehow have to teach this to our neural network once we got the big data set. You have to be patient, like in a lot of manners. Like I have been waiting for the prototype data set for a year. It took so much time for the clinicians to label all this data. We are still finding issues when we're talking about the final data set. For example, once you're in the clinic with a stroke, you can also have some complications, and then we need to do the follow-up imaging, and you may have a second stroke. Stuff like that can happen. And then they need to find the proper follow-up imaging. And it seemed that in our test data set, this went wrong a couple of times. So you need to be patient to get a really nice data set, because if you're not patient, you will get a messed up data set and you will not be able to predict anything on it. And you need access to a server. I mean, I don't know how you want to proceed tomorrow with your hackathon, but if you really do some 3D training of medical imaging, you need a server. Like it takes 2 or 3 hours on the server for us to do one test run, and you have to do so many settings and you can try out so many things. You have to rerun this over and over again. So you need a server if you get a nice data set and if it's at a certain size. All right, so thank you for your attention. If you have any questions, post them to me, or if there's some further question coming up during the next days, contact me via email. And neural networks will be everywhere. Thank you.
Okay. Thank you so much, Christina. I love that meme at the end. Thanks. So we have some questions. I think that talk was, you can keep sharing your screen, it's fine. So I think that talk was extremely useful and practical and frankly, very pedagogical as well. It serves as a really nice recap on, how neural network works. Especially we went through some of the topics in the previous 2 workshops, and tomorrow we're actually gonna have Dr. Farhad Maliki to talk about 3D augmentation on methods on CP segmentation as well. So stay tuned for that. And yeah, especially when you were talking about how to visualize the unit, how to visualize, the output of different layers. I found it extremely useful to verbalize that, because if you have any questions, we have some questions in the Discord channel. So we're gonna, so I'm going to ask Vasu or Jacques to monitor that and ask you the questions now. And then after that, you can raise your hand here on Zoom, and then we're gonna unmute you. So let's go. So who wants to go? Jacques or Vasu?
Yeah, sure. So
Go
one
ahead.
of the questions is on slide 2D. What is that colorful image? Is that the activation map? So is there
hold on oh yeah, the colorful image, that is the brain, the region map of the brain. So where you have these different areas, or the separation of the brain into different areas that have different functionalities. So it's just a color coding for every color encodes another brain area. And it's not about the activation map. Like the activation and saliency maps have actually been the black-white ones.
Great, thank you. And another question is, for your ROCs, do you think that you got such good results because of your large training data set or for any other reason?
I think we got this nice results because of the data augmentation, I would say. I think and on the other hand, you also have to say this is a very unbalanced problem. So lesion is usually a small part of the image that you're looking at. And everything that would be under 70% would be super surprising in accuracy, because assume you just predict everything's black in the image. And then you're probably right in many, many cases, because you only have, let's say, 10-20% of the image with the other voxels filled. So this is also one reason why you actually get, let's say, good-ish results right from the beginning.
Great, thank you so much. There's a few other questions. I think I'll let Vasu deal with that. Is that okay?
Yep. First of all, thank you for the talk, wonderful talk. And yeah, I really like how you combine multiple modality for lesion predictions. And first of all, I also have the question for myself. How did you deal with multimodality for various modalities you were having? Like, did you combine into a standard format or something of that sort?
So this is part of the pre-processing, which is actually done by our medical collaborators, and they are doing registrations. So their registrations register all the modalities so that they're all like positioned in the same direction and form. And what they actually also do, because we've been trying that as well, you can map brains into a standard brain. This is in that area a very popular transformation. And we wanted to figure out if this helps if we do this transformation before we feed the stuff into the neural network. It actually turns out that this does not really help for your information, but the registration, you have to do that, of course.
Makes sense. And we have some questions. So first of all, like, that's one of the question we are having.
Sorry, we didn't hear you, Vasu. Can you repeat that? And then afterwards, after that question, you can go to Dr. Anger and Samer here in Zoom chat.
Okay, so we have a question regarding how to crop the different data sets from multiple modalities. And maybe it's a very generic question, but and yeah, that's one of the question we are having here in a Discord channel and Zoom chat.
So this is also part of the pre-processing. I mean, the cropping somehow comes also with the registration process. What we also got from our medical collaborators, but we actually did not really use this so far in the training process, is something like a window where that slices down the area where you have to search for the lesion. So like a potential area where it's actually sensible to search for lesion, because depending on how you have rotated in the different modalities, there are some areas of the image that you cannot really use anymore because they're so much shifted and stuff like that. But we started with like, okay, let's just feed the stuff into the network and see what's going on, and then we can think about restricting the search radius.
Yeah, we have a follow-up question from the same attendee. So how did you manage the voxel size and planes from different imaging modalities?
Okay, so there's a standardization process going on pretty much. So you're getting there and do some interpolation and resampling of the images once you get them correlated into the right direction.
I see. Yep, and probably one other question we are having. So did you try with different channels for different modalities? If yes, then how?
There's something that we tried, but I do not really have results so far because it's still running on the server. In this unit that I showed you, we just made one thing because this unit is actually only made for one modality. And what we actually did is we used all the modalities and just glued them together and built up a long image out of it. And then we put it into the neural network, and after that we decomposed it. And what we are now doing is this early stage of the neural network, like the convolutional path, can actually be mirrored, and you mirror them as often as you do have modalities. So in our case, we would have 3 or 4, depending on if you use the parameter maps, different channels and or different convolutional paths of the network, and you also connect them, like interconnect these different paths so that they can actually talk to each other, let's say it like that. And then it goes down with like a multi-path convolutional path into that into this smaller bottleneck, and then you can deconvolute it again. And this is something that we're doing right now, because like actually just putting the values together like we did it so far is, I don't really think that this is the best thing you can do.
Yeah, and another follow-up question from the same attendee, like, how does this work for 3D and 4D time dependent data?
So the 3D is actually relatively easy to achieve, because you usually just set up like you have these kernels are usually 2D, or that's how the traditional kernels look like, but you can also have 3D kernels. And this is pretty, I mean, you just pretty much extend everything into the third dimension, because it's from a mathematical point of view, there's nothing fancy going on in this and at this stage. 4-dimensional depends a little bit on what you are looking at. If you use, if you have it, like I said it in this example, like a video, you somehow have to deal with the time as an input, because I can make 16 new channels and just put each of the images out of this mini video into them, but then I lose the correlation that this is actually a video and that certain pixels are connected via time. So in this case, we actually have to find a way how to model that into our neural network. And we will see how we do that. There are different options available, but we did not agree on one so far.
Yep, makes sense. Yeah, and we have some of these attendees which have raised their hands. So yeah, I would like them to ask their questions if they have. Yeah.
We'll start with Dr. Enger here.
Yeah.
I'm gonna ask.
Is your arm sore yet? You've been raising it for a long time.
But it was lots of interesting questions. Thank you very much, Christina. I have a question regarding your visualization software.
Mm-hmm.
Is it in-house and open source? And in that case, is it possible to share it with us and our attendees?
So we are working on that, like, and we're not saying we're working on that, we're like truly working on that, because we the idea is that we build a software that we can also give to our clinicians, and they can do clinical tests with it. And for that, we need to find a way to like make an X out of it and just make them install them, because no doctor will sit there and install VTK and all those things. So we do not have that software, but if you're okay getting a prototype that may crash, I can talk to my student and give that to you, because that was actually a web-based application.
Well, that sounds good. We are not afraid of installing things and making it work. So thank you.
Okay, and there will be a paper soon published, so it's right now in the editing process that actually goes along with this visualization part of the neural network thing that I showed you.
Thank you so much.
And I see that Anne has a follow-up question regarding the multi-channel approach. Do you have any references for that? If so, maybe you can send it to my way or something, or drop the link here or something.
I have references for that, but I have to look them up.
Sounds good. I'll remind you.
Do in one minute.
Yes. No, you have to do it now. No.
Yeah.
Or
Samia has a raised hand.
Thank you. First of all, thank you so much for the very interesting presentation. I enjoyed it a lot. My question is what are the methods to integrate information that's outside the images that might be very important for to improve the performance of the network? So for example, what kinds of treatment the patient got, if they got a thrombectomy procedure or they just got medications, maybe that would affect the lesion size at the end. Without that information, the network might make an erroneous prediction.
So we actually also will go into that direction, and what we are also aiming for, there's a score that the clinicians have, and it goes from, I think, 1 to 5. It's not as important what it says. It's like from bad outcome to good outcome, something like that, in the direction. And what you can do in that case is you can go to your bottleneck of the unit, and once you're at the bottleneck, you just toned down your entire imaging data set into very specific features. And then you can combine them with all the other things that you can imagine or that you can think of, let's say gender, age, whatever. And what you do there is basically using something like, not as fancy as a unit, just like something like a multi-layer perceptron or something. So you can just use the output in this bottleneck and put it together with everything that you like. Does this answer your question?
Yes, thank you.
All right. So that concludes the last question. Thank you so much, Dr. Gillmann, for your wonderful presentation. I'm sure everyone enjoyed it very much and you all learned a lot. So I'm going to hand the mic to Luca, who has actually worked with Dr. Deufel before, and I'm going to let him introduce Dr. Deufel right now.
Sure, I'm sharing the correct screen here.
Yep.
All right. Yeah, it's my pleasure to introduce Dr. Christopher Deufel to all of you. He is an assistant professor and a medical physicist in the Department of Radiation Oncology at the beautiful Mayo Clinic in Rochester, Minnesota. I highly encourage you go see it. It's quite the institution. And Dr. Deufel is also the chair of the research for the division in the medical physics at Mayo Clinic, and practice leader for brachytherapy in the Department of Radiation Oncology. He is also a wonderful mentor from firsthand experience. So I'm gonna give the mic to you now, Chris.
Thanks, Luca. Let me share my screen. Just to repeat, I am a medical physicist who assists with the technological aspects of radiation cancer treatments. And thank you, Luca, and the other organizers for inviting me to share my thoughts on how AI can be used to improve radiation therapy treatments for our cancer patients. The talk that I will be delivering, it's going to have 4 chapters. And so, one second. So the first chapter here is going to be a brief overview of radiotherapy and the definition of a medical physicist. And the second chapter is going to describe a special type of radiation therapy that's called brachytherapy. The third chapter will outline the current challenges in brachytherapy as I see it. And that last chapter, it'll actually be the biggest chapter, will present how machine learning and medical imaging can be used to overcome those challenges. And we'll have a brief interlude while Luca provides a specific example for how AI has been used in the past to help with one of our challenges. So let's start with chapter 1. This is a brief overview of radiotherapy and medical physics. So I'll start by saying that radiation is a very effective tool for killing cancer cells. And over the past 120 years, scientists have developed tools for locating cancer cells and pinpointing them with focused radiation treatments. Currently, there are 1.66 million new cancer diagnoses in the United States alone each year. And that leads to a 43% probability that a person develops cancer in their lifetime. Now, 2/3 of all cancer patients will receive radiation therapy, and 3/4 of all radiation treatments are for curative intent. So here are some fundamentals of radiation therapy. Now, first, radiation therapy is local or regional treatment, which means it's a lot like surgery. Second is that it's often combined with chemotherapy when the cancer has spread beyond a localized site. Third, patients are usually treated with a combination of surgery, radiation therapy, or chemotherapy. Just a few more. So the radiation dose that can be delivered to the patient is limited by the normal tissue toxicity, which can cause short and long-term complications. For breast cancer, these tissues would be, these are some examples, would be the lung and the heart. For prostate cancer, the rectum, the bladder, the femurs. For brain cancer, the brain, optic chiasm, the brainstem. And the pancreas, the liver, the kidneys, the bowel, the spinal cord. And finally, the tolerance doses, unfortunately, for those normal tissues, they're lower than what you really need to kill the tumor. So we have to be creative and we have to focus our radiation on the tumor so that we don't have spill out into those normal tissues. Very briefly, the mechanism by which radiation kills cancer cells is by ionizing the DNA base pairs or the backbone of the nucleus. So double-stranded breaks are considered to be lethal to the cancer cells, whereas those single-stranded breaks that you saw, so if I play that again, there's the single-stranded and we have these double-stranded breaks. The single-stranded breaks can be repaired, and so they're sublethal. There are three basic ways that we can generate radiation for cancer treatments. The first method is going to use radioactive isotopes. So this can be created from nuclear reactors, and the radioactive sources could be either placed kind of in or on the tumor, and we'll get to a little more description of that with brachytherapy. The second type of radiation is a linear accelerator, and that uses a waveguide to accelerate electrons, and those electrons will impact a high atomic number target, something like tungsten, and that'll produce a shower of photons, which we collimate to a desired shape and focus them onto the cancer. And the third method is a little newer, it's a little fancier. And so cyclotrons or synchrotrons are going to produce heavy charged particles. So at Mayo Clinic, we accelerate ionized hydrogen, and that creates protons to very high energies. And we use magnets. This is a picture here from Mayo Clinic. We use these magnets to focus and collimate those. And in general, all three of these types of treatments are offered at Mayo Clinic. And it's because some patients are better candidates for one or the other based on the location of the tumor. So for example, if it's a tumor that we can get a catheter into, like a needle, or it's on the outside of the patient, then we might use brachytherapy. If the tumor is adjacent to the spinal cord or other healthy tissue, we might choose proton therapy. And we also sometimes wonder if the position of the tumor in the body might change while the patient's breathing or has different amounts of liquid. And that might mean we need something a little more robust than proton therapy. And so maybe we use the photons. Briefly, if you're wondering, how do I become a medical physicist? You know, this sounds amazing. There are basically medical physicists are concerned with applying physics to identify and manage diseases. And it's a little different than your typical physicist because they have a clinical focus that is both immediate in timeline and it's applied in a manner that fits into the kind of medical care model. So for example, a biophysicist might study DNA repair and a DNA repair motor, while a medical physicist might study how a drug that's blocking DNA repair impacts the effectiveness of a specific radiation treatment. The medical physicists have a master's or a PhD degree, and they're roughly divided into imaging and therapy branches. The imaging physicists will interact with technologies such as PET scanners or MRI and CT, and radiation therapy physicists, on the other hand, they'll participate in medical treatments to manage or cure the cancer. And a medical physicist will receive formal training with a 2 to 3 year residency. So after they finish their PhD or master's degree, they'll go through a residency program, and then they're ready to work in the hospital. All right, so that's a little bit about how radiation works and what a medical physicist is. Chapter 2 is going to describe brachytherapy. So what is brachytherapy? And this is what I love to do in the clinic. And so I'll do my best to show you why I think it's really exciting. Brachytherapy is going to be internal or interventional kind of radiotherapy. And it's Greek from the word brachy, which means close. And so the radioactive source is going to be placed on or in or near the treatment site. So it treats cancer, think about it from like the inside out. and that helps it protect those nearby healthy tissues. A disadvantage of brachytherapy because of that is that it is invasive, and it does require a procedure to get the radiation inside of the cancer. So here's an example of an applicator that is used with localized breast cancer patients. And after a tumor is excised from the breast, the device will be inserted into the surgical cavity. It looks a little bit like an egg beater. And these peripheral channels, they all expand once it's inside of the cavity. And then we connect it to a robotic system that controls the radiation delivery. So the robotic system has, in our case, radioactive iridium that's welded to the end of a very flexible wire. And I'll show a video in a little bit of that process. And it uses motors so that it positions the radioactive source in different parts of these channels. And so this figure on the right, this shows the device inside of a patient, along with the dose distribution from that patient, and it's hyperlocalized. All right, so the next one here, I'm just going to go to video here, computer pop up. Okay. I think I have to do something special to share sound, don't I? Go to more.
Yeah, you could unshare your screen right now, and when you share again, click share sound on the left bottom corner. So you can unshare right now and then do that again.
Stop sharing. Okay.
Yeah, stop sharing.
All right.
And then share screen again. And before you click on your screen yet, see the left bottom corner, there is a share sound. Do you see that?
And share sound, perfect. Thank you.
Awesome.
I don't remember which password they want.
The expedited brachytherapy treatment process is for low-risk, early-stage breast cancer patients and involves a single surgery. First, special dyes are injected to identify any cancer cells that may have spread beyond the tumor site. That allows a pathologist to immediately screen the lymph nodes under the arm and a safe margin of tissue around the tumor, while the patient is still under anesthesia. Once the all-clear is given, the surgery continues with a second incision to insert the brachytherapy catheter and expand it, filling the lumpectomy cavity. The very next day, the patient's radiation plan is mapped out. The following morning, a computer-controlled robotic machine manipulates a radioactive seed, smaller than a grain of rice, within the implanted catheter. The seed stops at different locations for varying amounts of time, thus shaping the radiation dose. Unlike externally delivered radiation, brachytherapy strikes the target area more precisely, without passing through healthy tissue. For the Mayo Clinic News Network, I'm Dennis Doda. The expedite.
All right, let's go back to, so that's the robotic treatment. The next bit here is just a little bit of an overview. So this is like kind of a broad spectrum of the things we can do with brachytherapy. And so it's an effective treatment for many sites. And I've listed here prostate and uterine, cervical, vaginal cancer, breast, skin, soft tissue sarcoma, liver, bile duct, rectum, tongue, lip, cheek, ear, nose, vessels. And there's a pattern here. It's kind of anything that you can access easily to get a catheter into. And the brachytherapy treatment has the following workflow, and this will become relevant when I talk about challenges and the AI applications. So the whole process is done usually in a continuous session lasting from 2 to 4 hours, and then the patient goes home. So first you place an applicator, and that gives you an access point for your radiation. Second, the cancer target and the nearby healthy tissue are identified in images. Third, the applicators have to be identified in the images. Fourth, we run a mathematical optimization to determine where and how much radiation to administer. Fifth, the radiation plan is reviewed and revised, perhaps even, and the quality assurance tests are performed. And then finally, we administer the radiation. Okay, so we've gone through the first chapter, which is what is radiotherapy? How does it work? The second is what is the specifics of brachytherapy, this form of internal radiotherapy. So now this third chapter is going to be the current challenges in brachytherapy. And I'm going to highlight 3 of those, and then we'll go on to our final chapter. Okay, so time. Time is the first challenge that brachytherapy faces. And these procedures are lengthy, which means more anesthesia risk for our patients and cost for our healthcare system. The procedures themselves, they take a long time because there are many steps which require currently manual processing. So for example, in order to digitize one of these applicators, which we use then for our instruction set, a human being using state-of-the-art commercial systems has to do all of this stuff. So they click the mouse twice to create a new applicator. There are 5 manual entries to set properties. They reorient the applicator, so they want to get the image planes so they can see the applicator well, and it took me 4 reorientations. I had to zoom in and out 3 times. I want to know where the tip of this is really well, because actually I need to know where the inner lumen is and not just the outside part of the metal. And so it took me 4 clicks to create this profile to see that. And then it took me 12 clicks to mark the inner lumen. And so this is similar time challenges. All in all, this takes several minutes for each applicator, and a patient might have 20 applicators inside. And similar challenges exist for those other steps in the brachytherapy process. The second challenge is safety. And this image summarizes how I sometimes feel about the tools we have to ensure that our treatments are safe. And we rely very much on skilled and trained staff to check each other's work in order to provide our quality therapy. So I think the tools can be improved in such a way that it better supports our staff and provides a safety net throughout the process. And that's how I think AI can come into play. Personalization is our final challenge. That many of our patients are similar, but no 2 patients are the same. So how do we transfer learning from one patient to the next and make medical decisions at the same time that are customized? Right? So those 3 things: time, safety, personalization. Try to keep those in mind as the challenges. So here's our finale. How do we manage the challenges in brachytherapy using medical imaging and machine learning? The first application is organ segmentation. I mentioned in the process that we want to tell the mathematical system, here's where the organs are, the target and our healthy tissues, and here's where the applicators are. So that first step is organ segmentation. And the plan will be optimized to deliver a high dose to the tumor. So let's say the tumor's in the prostate here, and a low dose to the surrounding tissue. So low dose to the bladder, the rectum, the urethra. And the physicians will contour these structures then in order to perform that optimization and solve for the best places and best amounts of radiation to put in. And the images that we use include ultrasound, shown here, MRI, and CT. And the organ delineations that you see here, they're kind of different. The applicators and the organs look different in each of these modalities, so they each have their own challenges. The second application for machine learning is automating the applicator digitization, that kind of manual click process that I described earlier. And the applicator digitization tells the system where it's possible to position the radiation. In medical imaging analysis, for example, could we write an algorithm that finds the bright objects in a CT scan? This is an image of a cervix cancer patient with a metal applicator. This is called a tandem. That's placed inside of the uterus, and the radiation source, as a review, will pass through the applicator in order to administer the radiation. And in this case, you can have a simple method for identifying the applicator, just using pixel values that exceed a threshold for bright objects. And you can do that because the tandem is much denser than anything else around it. And we used a thresholding approach like this to write an automation algorithm for this type of applicator in our clinic. And this is the publication we had here. And this is an example of a screenshot of the user interface. The algorithm, briefly, it starts with a threshold of high density regions. And you can see there are 3 metal applicators in here. And next we use a density-based clustering algorithm. This is very simple machine learning to cluster them into 3 applicators. So take all of these things, but I want the 3 applicators. I don't just want all the little dots. I want them actually to be organized by their applicators. And then finally, we have to write those results into a format that other systems can read, so that we can use it in our clinic. And that requires locating the inner lumens and converting those results into a file with a DICOM format. All right, so putting this into the context of those challenges, those 3. So remember, we talked about time, safety, and personalization. So we can ask, did it make it faster and safer? And so first it was 10 to 15 minutes faster than the human could do. So check, we can check off that it improved efficiency. And then as far as safety goes, it provided a forcing function for applicator properties. So there's no human typos to lead to mistakes. And it provided very consistent and reproducible digitization. This is difference from the human expert from 0 to 1 millimeters. Our tolerance is always actually 2 millimeters. So we generally were in the tenths of millimeters here. So this is fantastic. And so we can check off that it made things safer. Now, what is the role of AI and what role might advanced learning, machine learning play in digitization? An applicator itself can be differentiated by much more than just its density. The spatial location, the size, and the shape are also important. So these images below, this is an axial and a sagittal image. So a cross-section, like if you're looking at the screen now, axial is like a cross-section like this, slices through the patient, and sagittal is a cross-section like this, where you're kind of taking different cuts. And what you can see in these is that there are other bright objects that are even brighter than the catheter. So there's a gold seed that's a kind of a reference marker that was placed inside of the prostate. There's a urinary catheter and there's a Foley here that we can see. And so the problem is trickier because of those other dense objects in the field of view. So Luca worked with Mayo Clinic on a deep learning solution for prostate treatments using those CT images. And I'm going to stop sharing and Luca's going to talk briefly about his work.
Yeah, thank you. That's a perfect introduction, actually, covering all of the background necessary to understand this part. Yeah, so at the Mayo Clinic, I had the privilege of working for Dr. Deufel, and we developed an automated digitization approach for applicators for brachytherapy. And why that's relevant was described previously. But the purpose of my talk is also in part to show you a little bit about how we can really think about different architectures and how to fine-tune hyperparameters and things. But a lot of the time, using some algorithmic approaches and just some common sense can also go a long way for our AI-based approaches. So our paper is titled Approaching Automated Applicator Digitization from a New Angle. Or at least it will be. For now, it's a presentation. The first question is, why do we automate the digitization at all using AI? And this was previously mentioned, that the time concern, there's a possibility that there's human error, and inaccuracies can negatively impact the treatment quality. That's why Dr. Deufel was mentioning it's so important to get the tip positioned correctly, for example. And then the other reason is, well, we now have the computational resources and software to make it. So the digitization process we employed worked in 3 steps: data preparation, AI training, and automated digitization, each of which I'll now explain. For the data preparation, and this is where all the algorithmic parts come in, we first reduced the field of view to a smaller centralized region where we cut out a cubic volume from the CT images, which really increased computational efficiency and detection accuracy by eliminating just unnecessary regions. Then we resampled to a higher and uniform resolution, which is standard practice, and going to a higher resolution will improve your detection precision. Next, we had to actually convert the manual digitization into a format that a UNet, for example, can segment. And Dr. Deufel mentioned when a physicist digitizes an applicator, they will place points along the inner lumen of the applicator on a CT image. And we took those points and simulated the cylindrical volume between them and found the cross sections with each CT slice, and we're able to create a mask of where the applicators are in the CT images that way. And finally, and this is kind of where the novelty of our approach comes in, we reoriented our images from the axial perspective to the sagittal perspective. And I'll touch a little bit on that later. We use a two-dimensional U-net architecture. Dr. Gillmann gave us a nice little introduction into how that works. And here's a testament to its popularity, because we used it as well for something completely different. And there's a bit of a debate in the literature about whether to use 2D or 3D. And we chose a 2D, even though when you only see a single image as an input, you have less contextual information, because what a 2D approach allows you to do is just use much higher resolution, and you have a lot more computational efficiency that way. We use some training parameters here, like a dice loss function. Our train test split was 27 in training, 10 validation implants, and then we had 20 patients that didn't appear in any training or testing validation, and the number of needles that were digitized in every implant ranged from 7 to 20. Now, here's the third step, which is the automated digitization. Once the U-net sequentially generates two-dimensional masks, we glue those together into this three-dimensional volume and apply a threshold to create something binary like you see here. Now all we know is where the applicators are and aren't, so we still have to cluster them into the individual applicators in our second step. And then in our final step, we separate crossing and merging applicators and eliminate any of the confounders that may have accidentally been picked up as applicators. And again, this is where, for example, a lot of algorithmic work happened. And this, again, emphasizes why in the last workshop, for example, we took some time to think about how do we manipulate images and masks algorithmically. So then we identified the inner lumen, which are represented here, and compared those against the manual digitizations. Here are our results. You see that we have reduced the total time it took to do an entire, digitize an entire implant, so all 7 to 20 applicators, down to about a minute. And the tip and shaft errors are below 1 millimeter. And these results here, a tip error of negative 0.1 plus or minus 0.6, and a shaft error of 0.13 millimeters is actually the best geometric agreement that has been reached in literature to date. And the reason that we believe we achieved these sort of high performing results is that we reoriented our images. Instead of using the traditional axial view, which again, you kind of see the different planes here if the names are new to you. We use a sagittal view because in the axial view, applicators appear as these small dots that are very hard to discern from other bright things like the gold seed that Dr. Deufel was showing earlier. Instead, we look at it in the sagittal view, and now applicators appear as these long, thin objects, which are a lot easier to discern from confounders such as gold seeds. And we noticed that the U-net that we trained actually got similar segmentation scores. So we use a dice loss function to score how good the segmentations were, and both the axial approach and the sagittal approach yielded similar dice scores. However, when we glued all of the two-dimensional masks together, we saw that they both seem to have data loss in very, very different ways. In the axial, using the axial approach, you would have applicators that just go missing for a few slices. which makes it nearly impossible to digitize the inner lumen later. So here an entire chunk of the applicator is missing, whereas here it's present. Similarly, you have a lot smoother contours along the Z direction in the sagittal view, whereas here they seem kind of chunky. And a final example is this gold seed that was that you may be able to see here, that was picked up by accident using the axial orientation, whereas in the sagittal orientation, where you see applicators as long, thin objects, you didn't have this gold seed that was accidentally contoured. So simply changing the view angle made a very, very big impact on how our models performed. Yeah, so in going back to the dice functions, what that means is, even though you may over contour or forget to contour some of the image during the deep learning based part of the workflow, in the axial view, that can look like missing entire chunks or missing entire applicators in an image. Whereas in the sagittal view, you may have over or under contoured an applicator in its width, which may create slightly thinner or broader applicators, but they're much easier to digitize in the following step. So that's why we achieved these results, and it goes to show how important it is to have these sort of common sense bring common sense into deep learning training, and as well as algorithmic approaches for to aid in the deep learning approaches. Yeah, and thank you to everyone that made this work possible. If you have any questions, you can ask in the Q&A section or email me afterwards. And I'm going to hand it back to Dr. Deufel.
Thanks.
Right. Thank you, Luca. Thank you, Dr. Deufel. Oh, sorry.
That's all right. We're going to jump back in. I have just a couple more highlights, if that's okay. All right. I know we're running a little bit late, so I'll try to get through these. So the third application for machine learning can be improving how we calculate dose. And so specifically, we're looking for faster methods to model the impact that these tissue and material and applicator compositions have on energy deposition inside of the patient. And our state-of-the-art models, what they do is they model the physics principles, and the solutions therefore can take a long time. And machine learning can provide a shortcut by finding patterns in the relationship between tissue density and the energy deposition. The fourth application is how we optimize the locations and amount of radiation for our treatments. So optimization is what we call that. And it's currently handled with mathematical algorithms where we enter objectives and priorities for the dose to the tumor in nearby tissues. And I'll try to walk you through why I think this is an iterative, kind of like time expensive process. And it's mainly iterative because there are no two patients that are alike. And so the objectives and priorities need to be adjusted until the plan strikes an ideal balance for the current patient. So our physicist will first establish where inside of the applicator the radiation sources should be allowed to dwell. And so here in bright green, you can see these are the spots. We have three applicators. It's called the ovoids and the tandem. Three kind of applicators in the green spots are where we said we'll allow radiation to be. Next, the physicist will enter some dose objectives and priorities for the contoured structures. They'll go into this little window, they'll type a bunch of numbers in, and they hope they don't make a mistake. And then 1 to 5 minutes later, what we'll get is locations and amounts of radiation that can be referenced by the machine. And then the staff can review the plan and the results. And most often this process is repeated a few times until the healthy tissue and target doses are balanced just right. Now the AI analog would bypass the mathematical optimization. So instead, the source locations and the times would be established by a deep learning assessment. And we'd train the model based on past practice. And in essence, we'd find out how the patient's anatomy compared with others, and we'd look for patterns. So it wouldn't be a traditional optimization algorithm, but it would be consistent with past practice, which was done using these iterative optimization methods. Now, closely related to optimization is plan selection and the personalization. And I think that's something also that AI can assist with. So each patient has different anatomy, and it's easier to deliver a high dose to the cancer target for some patients than others based on where the cancer is. And our MDs are responsible for striking the perfect balance between target and normal tissue. And we hope that our staff always find that ideal balance, but what if they don't? Can AI provide decision-making support by presenting the best plan and comparing it with past patient results? So for example, maybe plan 1 here is the best for cervix cancer here. This is one where you have less bladder dose and less target dose. Or maybe plan 2 is better, where there's more dose to the cancer, but at the cost of more dose to the bladder. And so knowing how you had patient outcomes and how your past patients turned out and what their dose distributions looked like, can you provide some guidance to the physician about what would be most appropriate and what are the risks of toxicity? So the AI might be able to find some patterns among patients to suggest a best treatment plan. And it is a challenging problem because the AI not only needs to account for the differences in internal anatomy, but also the differences in the number and the locations of the applicators. So here are 2 different prostate cancer patients, and they look similar, but they have different numbers of needles, and the locations of the needles are different. And so it's kind of a different, it's like a whole layer on top of the anatomy that makes it a bit more complicated. I got one more for you, and then I'll be done. So the last application for machine learning and brachytherapy is a tool that could extract features from the medical record and the images to maybe uncover disease characteristics which better predict toxicity and local control. So we could extract those to create a curve like this one on the right. And this curve would show you the probability versus dose that you have damage to the normal tissue or tumor control. So maybe one of these curves looks like rectal fistula or urinary stricture. And one of these is cancer recurrence. And so the physician, if we could figure out what these curves look like for our patients, we can start making decisions which are based on the probabilities of bad things happening and have conversations with our patients up front about how they want to strike that balance themselves between going for cure, but potentially having some other risks. So for summary features, radiation is a widely used and effective treatment for localized cancer. Brachytherapy is a form of internal radiotherapy, which has the advantage of reducing dose to healthy tissue. Third, our current brachy workflow has challenges in efficiency, safety, and patient personalization. And finally, many of these challenges might be overcome or improved with medical imaging analysis and machine learning tools in the sort of way that Luca provided an example. So thanks, that's all I have.
All right, thank you so much, Dr. Deufel. And also thank you so much, Luca, for your wonderful presentation as well. You have achieved a lot in your undergrad, and it's really, really impressive. And I'm very happy to be working with you as well. So you should be really proud of it. And so we have some questions from Discord. And maybe Vasu, you can ask a few questions, then we'll have to move on with the rest of our presentation, and then everyone can migrate to GatherTown. Vasu, no, not Vasu. Jacques, are you there?
Yeah.
Sorry.
So one question is, how do you translate XYZ coordinates into DICOM X, DICOM Y, and DICOM Z directions? Are there coordinates directly inputted into the TPS, or do you have to write new DICOM files with these structures?
That's a great question. So there's kind of a process where you move from reference frames. So let's say you start with a CT image. A CT image has a native image reference frame. So it's got a center, and that center would be kind of your DICOM 000. And all of the coordinates are with respect to that CT scan. Now, if you choose to crop the image, so let's say I'm going to crop into the middle and maybe even resample, I now have to keep track of those adjustments. So my new 0, 0, in my array is a little bit different. It is kind of shifted. So I have to keep track of that spatial transformation, which is just plus X plus Y plus Z. So what are those deltas? Similarly, if you rescale it, so if you resample your image set to a finer resolution, you have to keep track of how you multiplied that or divided it. And so in the end, when your AI gets a solution on an image set which was cropped and resampled, you have to figure out how to rescale it back to what it should have been and move it back to the DICOM origin. So those transformations are actually really straightforward. Now, when you write the file and you write a DICOM file, you can either write it in DICOM format, or what we've been using for our commercial system is a backdoor. So you can either use an API or they have an XML. So we have a very straightforward process where I can create applicators in an XML format where I tell it channel 1, and here are the locations of the channels for channel 1. So there's actually, our system has a nice backdoor that we can skip the DICOM format if we want to, or you can write it into a DICOM structure file. So we'll take a file that comes from the vendor. So just like the CT file that comes in there, we have another file called a structure file, and we can write those things in there. And it kind of just depends on your comfort with writing DICOM files or writing XML files, but either of them works great.
Great, thank you so much. There's another question, which was, did you have to use finer slice thickness to achieve better reconstruction in the sagittal view?
Oh, that's such a good question. So the short answer is that that early work that I showed, so I'll pop this one up here. What we found is that to get the tips, to really get that sub-millimeter accuracy, it helps to have slices. Well, to reform, so our slice thickness natively was 1.25 millimeters. And so to get sub-millimeter resolution was a little bit harder if we didn't resample those. And so we resampled them to 0.5 millimeter resolution. And what I found is that when I did that, I got a few tenths of a millimeter better. It did a little bit better job on the tip locations. So the answer is kind of, it depends how picky you are. So I don't think you have to resample them if you're satisfied with the resolution that you're getting on the output. But it is a parameter you can play with, and it doesn't cost much except computing time. So you kind of get a choice. The finer you resample it, the bigger your images are and the longer it might take to process, because you've also created more slices. But if you've got a fast computer or you're patient, then the training can be done pretty efficiently. From the model running standpoint, it's not a big deal. It runs almost equally fast with low or high resamplings.
Thank you very much. There's a question for Luca, and it's, have you used parasagittal planes or true sagittal planes for segmentation?
Well, maybe Dr. Deufel, you can help me with the terminology here, but the parasagittal planes are planes that are parallel to the sagittal plane, as the name would suggest. And
they're a little bit different, I think. So I think parasagittal, if I remember, might be like an arbitrary plane, perhaps. Maybe we could ask that question. Are they asking, did we go strictly in these cuts, or did we maybe go at an angle? And we find that, like, we look for where the applicators, and we try to intentionally go parallel to some of the applicators.
No, so we went with I guess then the true sagittal planes, the planes that were actually aligned. We didn't reorient or rotate the volume at all. We just took I guess the true sagittal plane in that sense.
It's a great question, though. I've often wondered whether or not it would be helpful to kind of pre-process and give it cuts which go right along needles, right? And then ask it to find needles based on cuts that show a needle really beautifully, or even bend, right? It might not even have to be a line. It could be a curved plane through the object.
Yeah, and then the question becomes, how do you automate that reorientation? Because if you have to do it manually, you no longer have a fully automatic approach.
Exactly. So we chose a simpler approach.
Yeah.
I think that's pretty much all the questions that were asked on the Zoom and the Discord. So if there are any questions, maybe participants can raise their hands.
Okay.
All right.
If not, then I will just share the closing slides.
Oh, wait, don't go yet. Don't go.
Yeah, don't go yet. There is an important announcement at the end. Again, first of all, thank you to all of the sponsors. TransMedTech, McGill, our own medical physics department and our own lab, the Jewish General Hospital, Alpha Tau, Comp, and last but not least, GatherTown, which we will make an important announcement about in just a few slides. Eugene, do you want to do this one?
Yeah, this one just real quick. I sort of mentioned it at the beginning as well, in terms of how you can unmute your mic. So we can move on to the next one.
Yeah, so actually before we do this one and everyone jumps over, let's just take a minute really quick and do our land acknowledgement. So again, if you don't know the history of the land you're on, you can find out what the native people of your the land that you're on are using this nativeland.ca map. Just gonna click on that actually, and you'll see very quickly that it shows you exactly which tribes inhabited your land and still may inhabit the land that you are on. And we want to just say that today our virtual event is still based in Montreal, Quebec, which is the traditional territory of the Kanakahaga and is land on which has long served as a site of meeting and exchange amongst Indigenous people, including the Haudenosaunee and Anishinaabe nations. We acknowledge and thank the diverse Indigenous people whose presence marks this territory on which people of the world now gather. And we want to encourage all of you to learn and discuss about the history of the land on which you reside, especially this week, as there is so much celebration of people's country with Canada Day and the 4th of July. We just want to encourage you to also think about the history of your country and the land on which you reside. Yeah.
Yeah. So what Lucas said, very important for you to think about. And now to a little bit of a lighter topic. I reshared the GatherTown link in the chat as well. You can also find it in Discord, and then you just need to click on the link in order for you to join. And you can see that on the left side you're going to encounter this login page when you join there. You can edit your character, enable your mic and camera. And then on the right side, when you walk around on this virtual platform, you can see your someone who is virtually near you on those boxes above, and then you can talk to them. So you can walk around and mingle a little bit. All right.
Yeah.
So let's go. Let's go to that link. If you
okay, and again, for you those of you who have never used it, this is your opportunity to meet and connect with some of the other participants or ourselves. We may even, if our speakers are motivated, they may also jump over to GatherTown. You can just walk around, get close to people and kind of chat. It's a little bit more personable than a large Zoom call. But if you're not interested in coming, thank you for attending the presentation. A big thank you again to Dr. Christina Gillmann and Dr. Christopher Deufel for the wonderful presentations today. Really, really good stuff. I learned actually a lot of things from both of them again.
And thank you to our mentors as well, Vasu and Jack. You guys both did a very good job at monitoring the questions. Our audience is going to see more of you in the coming week. So please fill out your when to meet form for the tutorial that we're going to send out, and we'll see you there. Oh,
Oh, who launched this?
you did.
I did not.
All right, let's close it.
Yeah. Okay. Don't know
All
where
right.
that came from.
Well,
Okay. Well then, I guess we will jump over
Yeah.
to GatherTown.
awesome. See you there.
It might only work on certain browsers. I found Chrome is the one that works for me.
All right. Ciao, guys. I'm gonna close the session now and see you on GatherTown. Bye.